So I'd like to start with something today called solids of revolution as sort of a quick recap with a couple examples consolidating the topic. And really the idea here is that we're revolving solids. I see this name all the time. I always think it should be revolution of solids, but it's usually always called solids of revolution, which I find kind of awkward. But nonetheless, this topic sort of mainly comprises of sort of taking functions like suppose we had this type of function, and that could be anything. We would be given what the function is precisely, but the idea, despite what the function is to rotate it about the x or about the y. So if I were to rotate it about the x, then consequently I would have something that looks like I don't know, you could call it a cone, you could call it a funnel of some sort. And the idea is we want to find the area of this solid that we have essentially rotated around a particular axis. And so we want this area here. Now, of course, we could generate several such shapes with several different functions. Suppose if I wanted to rotate this not about the x, but suppose about the y. And if I did that, I would have something like this instead. Clearly we've only taken one function. Suppose we had two functions, right? Suppose we had, let's say we had something that looked like this and then something that looked like this. So these are parts of a grander function. Let's assume this one is x and let's assume this one is x squared. Rotating this about the x or rotating this about the y. So there are so many combinations and there are so many things we can generate by taking these functions and sort of spinning them around a particular axis. And so that's essentially what this idea solids of revolution is about, is spinning them about an axis, generating a solid shape, and then finding the area of that solid. This topic comprises of three methods. It's almost like series if you've been exposed to it before. The idea is to sort of see what solid is generated by rotating it about a particular axis and then seeing which method to use, which test to use almost. Although it's not a test, it's really just a methodology behind which method do we use to find the area. And we will see that some methods are better than others. But generally speaking, we have one of them, which is called a disk. Now, the disk method is essentially best for functions, singular functions. So, we have some use cases, right? The first use case could be, a singular function around the x-axis. Okay, this is the most general use case for the disk method. And then the formula for this, so how do you find the volume of a singular function that is rotated around the x-axis? Well, they have given it to be, the volume is, it will be the integral of pi r squared dx. Now, I usually like to write this as pi r squared dx, right? So this is sort of the end formula that I like presenting to myself. This also works, except it's not taking the constant out, so it kind of gets in the way. This is what we really want to focus on. After all, we'll be pulling the constant out regardless. So this is sort of the main idea for this one. Now, so the use case there is a singular function. And then naturally, we have one for two functions, right? I mean, we had one for one. What is the methodology behind two functions? So what you'll generally see is this method called the washer method. It's called the washer method. And the use case is when you have two functions rotated about the x-axis. Okay, now what I want to say is that you could use the washer method if you rotate about the y-axis, but if, our instructor actually said that he prefers to just use something called shells if you're around the y-axis. So I don't think we'll be seeing that. And so, I mean, those are two of the main ones, the disk method and the washer method. And this too has a formula, as you'd expect. The idea here is that the volume of two functions rotated about the x-axis is in fact just the outer radius squared pi, we're going to have pi on the outside, minus so it's going to be the outer radius squared minus the inner radius squared dx. Now, essentially what this actually is the integral of pi times the outer radius squared minus pi times the inner radius squared. But what this formula has done is it has factored out the pi from from these components here, and then it's eventually brought it down here. And so this is how we have an end result. Okay, and usually what you'll see with the washer method is that why we have this funky looking formula is that when you take two functions, let's say I had x squared, and then let's say I had x as well. When you take this bounded region and you rotate it about the axis, what tends to happen is you generate something called you're not going to generate a disk to get the area. You're actually going to have a gap here because there's sort of an empty space. You'll have that disk there, but it's not really going to be a whole unit. You're going to have this gap in between. So what tends to happen is you want the area of each disk, and so to get the area, you only want the area of the region that exists. You don't want the area of the gap. So what you do essentially is you take the entire radius, which we call the outer radius, and then we subtract off the inner radius, okay? Because if you subtract off the inner radius, what are you left with? You're left with this piece here that essentially comprises of the area that is tangible on this particular piece. So that's why we do the outer radius squared minus the inner radius squared, and that pi is essentially just a factored byproduct, as it were. And for what it's worth, they call it a washer because if you search up washer on the internet, you'll find these disc-looking things. And so this basically represents the shape that you would otherwise see had you, taken one of these discs that you would have to integrate. And so, you take the outer and you subtract off the inner. But much of this may be irrespective beyond the fact that this is the formula. So this is the formula for the washer method, and then for the disk, it's just this. Now the disk is far more easier than the washer, but I've learned to actually like the washer method more than the disk. Now there is unfortunately one last method, and this method is actually called the method of cylindrical shells, or often sort of cut down to just shells. We call it shells. And the idea on this one, so what's the use case? 1 second here. Now, the use case for this particular one is when we have, singular or two functions rotated around the y-axis. So, if you're going around the y-axis, you're more than likely going to use shells. And again, if you were to use the washer method, or if you were to use the disk method when you're rotating around the y-axis, what tends to happen is you're going to actually have to integrate with respect to y. Now, that means you're going to have to recalibrate your whole integral so that all the x's are y's, right? And so that's a lot of work. And the shell method, why the shell method is so special is it can help you avoid that. What it does is it says, okay, I'll let you rotate around the y, but we're still going to integrate with respect to x. So, let's not look over the fact that our instructor said that, he personally likes to keep with respect to x. Okay, so if he wants to keep with respect to x, that basically means that he has to stick to these confinements that, the confinement is if you're doing the washer method, and you want to integrate with respect to x, then you have to go around the x-axis. If you're doing the disk method and you want to integrate with respect to x, then you have to go around the x-axis. And if you still want to stay in terms of x while rotating around the y, then you have to go with shells. That's sort of the only way you can do that. Now, with shells, the idea here is to actually have the integral of 2 pi rh dx. And again, I mean, they like to put this, I usually take it out front to have that 2 pi and then the radius times the height dx. And so this is the formula for the shell. So let me go ahead and pull up a problem here. We'll build up in terms of difficulty, and hopefully you'll see that these things aren't too bad. So this one is to essentially have f of x equals x squared. That's our function here. And we're rotating about the x-axis. So if you've ever seen this function, it basically looks like this, where you have this piece here. But again, we're really only looking at sort of the right side of the graph here. So what we're really looking at is this guy here. And if we're rotating it around the x-axis, we're going to go this way. And so what tends to happen there is you essentially generate a solid that sort of looks like a funnel, right? It tends to look like a funnel. And what we're doing here is we're going back to our use cases and we're saying, okay, what does this fit? And what we see is that the disk method is perfect for singular functions around the x-axis. So naturally, we're going to use disks here. Before you actually rotate it around, it's actually helpful to draw what the curve was to begin with. It's sort of x squared, right? So we kind of have, instead of this rigid shape, you kind of have this parabolic shape, and then you're just rotating it around like that. And so this is sort of the shape that you generate. And what we're doing is we're going to take disks and we're going to run them through this area and add. We're going to do a summation of all the area of the disks, and that's why we're taking the integral. We're going to do an aggregation of all these disks, and if those disks are infinitely small and we're able to fit an infinite amount of disks, then adding all those disks individually should lead us to the area. So with that in mind, we use the disk method, and remember what the disk method says. It says pi r squared dx from a to b. And this question, I should also add, specifies from 0 to 1. So it's not the case that, the cutoff here is sort of from 0 to 1. So this is actually a pretty small point, and then we rotate that piece. So we're not rotating the entire curve, as it were. We're actually rotating a very, 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 confined segment. This is what we're looking at, right? Kind of like this, and then we're rotating that. So at any rate, sort of moving through the problem, we have pi from a to b, and again, that a to b was 0 to 1, r squared dx, okay? That's sort of the idea. The question is, what's the radius of the disk? For each of these disks, what is the radius? And the idea is that if you take the circle and then half of that is the radius. So for each one of these disks, whichever one you choose, half the circle would be the disk. And so this height here is actually given by the function. at that particular point. So let's say this is like, 4. For this disk, for this particular disk here, what's the radius? It would be 4, right? So that's the idea. And so then we come back here and then we would say, okay, well, this is pi times 0 to 1. And then we're not going to say 4. We want to generalize it for every single disk. If we say 4, then that's only about this guy. We want to say it for each and every single disk. And so the idea here is that for each and every single disk, the function will tell us what the radius is, because we're touching the function for each of these radiuses. And so basically this function is x squared, and therefore x squared will tell us the radius for any given disk. Therefore, the radius is x squared, but we're supposed to take the radius and then square it. And so then we have x squared squared, which is then pi times the integral of 0 to 1 times x to the 4th dx. And then we just solve this, right? So we solve this. So basically you could do pi and then you can solve this guy here. So whenever you're taking the integral, you add 1 to the top and you divide by whatever that is. So let's suppose you have x to the 5th and you're taking the integral. Just add 1 to the top, divide by whatever you added. And so that's what we're doing here. We do x to the 5th, divide by 5, and then on the bounds from 0 to 1. We plug in the top bound and then we subtract when we plug in the bottom bound. So we plug in the top bound, which is 1 over 5, and then we subtract when we plug in the bottom bound, which is 0 over 5, which is 0. And then all we're left with is pi over 5, because this multiplies, and that's our answer. So now we're looking at this question. Essentially, we take under root x, and then the idea is that we rotate it about the x-axis. So this is about the x-axis. So if you've never seen this graph before, or you're not sure how it looks, really it's just x to the 1/2. So if you have it sort of stretches out the parabolic shape a bit, and so this is how it looks. And so essentially, what we're doing is we're rotating this. This particular shape about the x-axis. So what do we generate when that happens? Well, we tend to have something like this. So we rotate this, and then it's gonna be like maybe you could say it's like the top of a wine glass, kind of, right? And so that's really the idea. I mean, it's you kind of just want to relate these. Just sort of relate these shapes. And yeah, this is kind of what we have here, right? And so what tends to happen now is you ask yourself, okay, well, this is the function, right? Y equals under root x. I've rotated about the x-axis, and that is best to use the disk method again. Remember that the disk method says pi r squared dx, so pi r squared dx from the bounds 0 to 1. And the idea is that we do, okay, well, what for any particular disk that I generate, what is the radius? Well, the radius will be half this circle. Each one of these disks, no matter how small or how big they are, they touch the radius of them. If I sort of cut what the radius is, it touches the top of the curve. So what this is from 0 to 1. It touches the top of the curve, and that curve is under root x. So it's under root x squared dx, okay? Now, what tends to happen is when you have under root x and you square it, if there is an index of 2, these cancel out. And so you're just left with x. Or you could think of it as under root x is just x to the 1/2. And if you square that, you then multiply the powers. That's x to the 2 over 2, which is just x to the 1st. And so it's just x. So this is pi 0 to 1, and then x here, and then dx. How do you take the integral of this? Well, if you're taking the integral of anything, let's say you're taking the integral of x squared, add 1 to the top, and then divide by whatever that is. So you can do the same thing here. You can add 1 to the top, divide by whatever that is. You're multiplying this by pi. Remember that after you take the integral, you want to evaluate it from the bounds 0 to 1. And so basically, you're doing the top bound first, which is 1 over 2, minus the bottom bound, which is 0 over 2, which is 0. Therefore, you're left with pi over 2. Let's take a look at another question. F of x equals sine of x from 0 to pi. The idea here is we want to rotate this about the x-axis. So this is going to be about the x-axis, okay? Now, the idea here is that, okay, well, we're looking at sine of x, but again, we don't want to rotate the whole curve. We want to rotate a part of it. So when you think of sine of x, what you should be thinking is, okay, you have a sinusoidal wave. And the idea here is that this is 0 and the end is 2 pi. It kind of replicates what we have on a unit circle where 2 pi is here, also 0 is here. And then the idea is when you go halfway of the circle, you reach pi. And so this is half of this circle. This is like the top half and this is the bottom half. So you get like a circle. So when you go half of the circle, you have pi, which is actually here, admittedly. And then when you're doing half of the circle, which is at this point, it's actually pi over 2 because you're taking pi and you're halving it. So this is actually, this point here is actually pi over 2. And then you have this point here, which is 3 pi over 2. Then you have 2 pi. And those are the important points because we want from 0 to pi. So really, we're taking this whole shape from here to here, and we are rotating it around the x-axis. So how is that going to look like? Well, you're going to have something like this. Okay, it's kind of an odd looking shape, but that's the shape nonetheless. It's best to use disks. Again, it's a singular function. We're around the x-axis, so it's best to use disks. So this curve, right? This curve is sine of x. And what are the radiuses, as it were? What are the radiuses touching? The radiuses are always, for any given disk that I could possibly draw, the radius of that disk, of that whole disk, will be sine of x, because the value of each of these points at any given disk will be putting that x value there, and you'll find the disk, what that value would be for the radius. So with the disks in mind, it's pi r squared dx. You pull out the pi, you have r squared dx. Now, what is the r? We said it was sine of x, so it's pi times sine of x dx, but sine of x squared. Now, what are the bounds? The bounds were specified. It's from 0 to pi. How do we solve this integral? It's a simple trigonometric substitution. Sine of x equals 1 minus cosine of 2x over 2. Therefore, this can be sort of solved by saying, okay, well, this is from 0 to pi of 1 minus cosine of 2x over 2. Now, that kind of looks more complicated, but why isn't it complicated? Because we can pull out a 2, so we'll have pi over 2, say that this is 0 to pi, 1 minus cosine of 2x dx. And then we can break this up individually. We can say that this is just pi over 2 times 0 to pi of 1 dx minus the integral of 0 to pi of cosine of 2x dx. We can do a u sub here. So we'll say u is equal to 2x, du is equal to 2 dx, and then we solve for dx. Dx equals to du over 2, and then we put this back, and then we basically solve. You'd have 0 pi cosine of u du, and then at this point, cosine of u is just, what's the integral of cosine? Well, it should just be sine, and so then you have sine of u from 0 to pi. Or actually you'd have sine of u, which is, in this case, it's 2x. And then, of course, you'd solve this part and you'd solve that part, and then you'd essentially combine them together to get your solution. But nonetheless, there are applications of disk that aren't as simple as I've clearly demonstrated. We've looked at disks quite a bit. Let's actually take a peek into washers. Remember, we said that a washer is kind of a shape that it tends to generate like this donut looking thing. And the idea here is, okay, let's demonstrate this with an example. Let's say we have, y equals x squared, and let's say we have y equals x. So how would this look like, right? So the idea is that, okay, you have your Cartesian plane. Let me draw x squared. You have something like, you have a parabolic shape kind of going like that, dipping down there. And then x, or actually, let me try to, oh boy. Okay. I don't know, it's not really kind of, okay. And then you have X, which kind of shoots through it, right? So the idea here is that, you know, this curve up, this curve here is y equals X, and this curve below is y equals X squared. And you can, of course, figure this out by looking at Desmos, perhaps. In fact, if anything, this should suffice. And the idea here is that we rotate this around the x-axis. And so we generate something that, you know, something that looks like this, where you have, you know, you have this curve and then, you know, it's cut off like this, and then you've rotated it, right? So you actually have like a mirror image of what you have at the top. And what tends to happen at this stage is you ask yourself, okay, well, you know, you have this shape, right? You have this shape looking thing. And I mean, how are you gonna, so you could try to do discs, but the idea is that you have this gap in between. And so what are you gonna do to tackle that? Well, you're gonna use washers. So this top here is y equals X. This bottom here is y equals X squared. And so the washer idea is that, you know, you have pi times the outer radius squared minus the inner radius squared. And you can actually rewrite this to be the top function squared minus the bottom function squared, because that's the relationship. You know, the outer radius will always be the radius that is touching the top curve, right? Because if you have this as your radius, okay, you have this as your radius, or this is your entire circle. And then what you want to do strategically is you want to be able to, you know, take this entire curve from here to here and then subtract off this portion, because that's essentially, you know, the gap. This is the gap. You want to subtract off that gap, and you only want to keep this top guy here. So you can strictly abide by the formula, or you could think of it conceptually. But if you were to flatten this out so that it's facing you instead of, you know, being like this, if you were to just sort of turn it around on its side, you'd see that you know, you can draw a shape from the center of it all the way to the end. But, you know, you want to be able to take the whole thing and then subtract up just a part of it to be left with the thing that's tangible, that's real. And so on these lines of top function minus bottom function, the idea is to then say that, you know, that, okay, well, I'm going to do pi, and then I'm going to take the top function, which is x. I'm going to square it, and I'm going to subtract off the bottom function, which is x squared. So I'm going to have to say x squared. But remember, the bottom function is squared. Now the bottom function is x squared, but since the bottom function is squared here, it should be x squared dx. And so that's essentially the idea. And then to simplify this down a bit, you'd have x squared minus x to the fourth dx. That's essentially the idea. And you would solve this, and then you'd come to a conclusion. But what about the bounds? And I forgot to mention what the bounds were of this function. So, I mean, you could look at it here if you were to take from 0 to 1. I mean, where they intersect is essentially where those bounds are. But how you can find the bounds without having to see where they, without having to see a graph, is you can set the top function equal to the bottom function, or the bottom function equal to the top function, and then solve for the x value. So, I mean, the top function in this case was what? It was x, right? The bottom function was x squared. Irrespective of bottom or top, you can just take both of the functions, like x squared and x, and then solve for x. So how would you solve for x? Well, perhaps you'd you know, take this guy to this side and set this equal to 0, right? Basic algebra 1 stuff. Maybe you'd factor out an x, right? This is called the zero product property. If you have two things multiplied to each other and that's equal to 0, then one of them must be 0. So you can set x equal to 0. That's one of the bounds, which we've confirmed here. As you can see, it is in fact x equals 0. Then you can do x minus 1 equals 0 and then solve. So x will equal 1. And we can see that that is also a bound. So this basically will resort to doing pi times the integral of x squared minus x to the fourth dx from 0 to 1. Again, when you're doing an integral like this and they're added or subtracted, you can take the integral of them individually. If I had x squared plus or minus, x to the fourth dx, I can just do the integral of x squared and then just add that to the integral of x to the fourth. Same idea here. So we'll just go through and then we'll say, okay, well, this is just going to be x to the third over 3 minus x to the 5 over 5. And then from 0 to 1, we would plug that in and then multiply it by pi. Let's take a look at y equals x to the fourth and y equals under root x. Let's see what's going on here. So we want to rotate about the x-axis. And so if you were to graph this, you'd actually see it looks just like this. This is the x to the fourth, and this is the under root x. And you can see the bounds are also clearly depicted. They have this bound meets at 1, this bound meets at 0, and you'll often see that that's the case, 0 and 1, because they don't want to, they're focusing on having you solve solid of revolutions, not getting too bogged down with the algebra. But nonetheless, this is a washer problem. We have two functions. That is an alarming use case. And since it is a washer problem, we do the integral of the outer squared minus the inner squared. And then we multiply that by pi from a to b, which we know is 0 to 1. You can take x to the fourth equals under root x, and then perhaps you could solve for these bounds. You'd have x to the sixth here equals x, and then you would eventually reduce this down to being 0 and 1. And eventually you would get to a point where you can then look at this shape and you can say, okay, well, if I have this shape and it's kind of this funky looking thing where, it goes like this and it goes like that, and then you revolve it, you'd have sort of like this lotus looking thing. And the idea is you take the whole line, the whole radius, the outer one that touches this top curve, which we know is x to the fourth. And then underneath that curve, we have under root x. And so we take that top curve, right? And we're just sort of just following the formula. We take this top curve, x to the fourth, and then we say, okay, that's going to be the designated outer radius. So it's 0 pi. It's going to be the top curve, x to the fourth, squared minus the inner radius, which in this case would actually be a very, very small portion, right? If we're looking at this line, this whole entire line, then this inner radius would be actually very, very small, right? But nonetheless, it would be designated by, it would be designated. So this top curve is actually, the top curve is actually under root x, and the bottom curve is actually the x to the fourth. So essentially what we should have here instead of what we have now, just a quick gut check, is that we should actually have the bigger curve, the top curve as the outer radius. So it should be under root x squared minus the inner radius, this one here, x to the fourth squared dx from what it seems to be 0 to 1, right? And we would solve this, and so we would say that this is pi, and then these would sort of cancel out, right? You're sort of simplifying the integral. This is going to be x minus x to the sixth dx, and then you can go through and then solve this integral. We would have pi 0 to 1, where we would have pi times x squared over 2 minus x to the seventh over 7, and then this would be evaluated on the bounds 0 to 1, and then that's the idea. So you'd eventually do this. And it shouldn't be too difficult because you have that 0 there, so that takes away a lot of the the algebra, and that's actually why it's done a lot of the times, is to take the algebra out of it so you can focus on the volume of a solid problem. So for this next question, we're actually looking at two functions. Yet again, we're looking at y equals, and actually let me sort of just do this here. But nonetheless, we're looking at y, let's see. We're looking at y equals 2x squared, and we're looking at y equals x cubed. We're not given the bounds, and we're rotating about the x-axis. So since these are two functions that kind of look like, a, you have a parabolic, the y equals x squared portion, and then you have a cubic. And essentially what happens with these is they kind of meet as they curve, they kind of meet at some point, and then they kind of just, do their own thing. They continue in that pattern. And so if you revolve this is characteristically what we would call a washer problem, right? It's a washer problem because we have those two functions. And the idea is that, if you were to draw a disk, you'd actually have a gap, right? And so you take that gap out, and then you're like, okay, I want the area. So I'll take the whole thing and I'll subtract off the inner piece. So you take the outer squared minus the inner squared in terms of the radius. So for the washer, as I said before, it's pi outer squared minus inner squared dx. And so the outer is usually governed by the top function, which in this case is actually 2x squared, as it turns out. So it's going to be 2x squared minus the inner function, right, which is this guy down here, which is cubic. So it's x cubed squared, and you're doing pi, and then you're doing dx. So what happens here is you have pi, and then 2x to the fourth minus x to the sixth dx. And what are the bounds, right? So I said you can find the bounds are where the curves intersect, right? So it's this bound up here at the top, 2,8, or if we're talking about the x's, it's 2, and then down here as well. But how do we arrive at those bounds? I said you can set the functions equal to each other and then solve for the x. So you can set 2x cubed equal to the other guy, which is, or actually 2x squared rather, 2x squared minus x cubed, and then you can solve for x. So maybe you'd factor out an x squared because we do have that common between both of them. And then you're doing 2 minus x because x cubed and x squared, that leaves us with 1x. That equals 0. So that means x squared equals 0. And this guy here also equals 0. And then this equals 0 because if we take the under root of both sides to get rid of the 2 here, those cancel out, and under root 0 is just under root 0. So you're left with x equals 0. Over here, we can take minus x. We could subtract 2, right? And those cancel out, and then x equals 2. And so we have x equals 0 and x equals 2. So those are the bounds. So we're left with pi. And again, we said 2x to the fourth minus x to the sixth. So we have 2x to the fourth minus x to the sixth dx. And then we solve this for 0 to 2. How would you take the integral? You'd say pi times 2x to the 5 over 5 minus x to the 7 over 7. And then you'd evaluate from 0 to 2, multiply that by pi, and that would essentially be your answer. Let's take a look at this problem now. And the idea is we're introducing sine of x and y equals cosine of x, right? So really what we have here is something that looks like this, which I think is a little too enormous. But the idea is that, this is what we're dealing with. We're dealing with cosine, and we're dealing with sine. And the idea here is to, let's see, that may be the wrong graph because I think it's maybe offset, but nonetheless, what's happening here is you have sine of x, and sine of x behaves as it usually does. And then you have cosine of x, and cosine of x actually it comes from the top, kind of like a bell curve, but sort of flipped on its side, as it were. And the idea is that what you're doing is you're revolving it around pi over 4. Let me see if I can show you this. So as you can see, this pi over 4 part actually lies right in the middle. And again, I mean, we shouldn't necessarily need a graph to demonstrate that fact. It's sort of, I actually added one here to them. I'm not sure why. I was thinking about something, but nonetheless, this is sort of a misleading image. But the image that I've drawn is essentially what what we should be following more closely. And the idea is that this pi over 4, it's actually here, pi over 4, and we're rotating that region. So we're taking this region and we're not just rotating it about the x-axis. Actually, this time we're rotating it about y equals -1. So we have this y, so -1 is here. If it were x equals -1, I'd draw something like this, right? X equals -1. But since it's y equals -1, so -1 lays somewhere around here, and we have this boundary and around which we're rotating this shape. So how would that look consequentially? We would have a shape that goes like this. We know we have our little like shark tooth looking thing, where we have the sine like that, and we have the cosine like that, and it's cut off at pi over 4. And that point, pi over 4, is where the threshold is. So we don't really necessarily have to draw everything else after that. And then that line, y equals -1, can be thought of to be here, and then we're rotating it around that around that line, so that we have sort of this symmetric type thing going on. So I mean, there we go. Right. And I mean, that's really the idea. And what are we looking at for, we're looking at two curves, right? Two curves that's around the x-axis. That's a clear washer problem. And so, if we drew a disk, it would be empty from the middle, right? It would be empty from the middle, kind of like this. So we would draw it, it would come down, right? But it wouldn't necessarily have, like, this middle piece would actually be a gap. So, this whole, everything inside here is actually just a gap, right? And so we can think of this as, like, if we were to flatten it out, we would have a gap like that. So, and it's being ran through this shape. Now, the point of contention here is, how do we get this formula, given that we're not just rotating it around the x-axis? This time we're rotating it sort of around -1, so it becomes a little problematic. But it's helpful to remember that this guy up here is cosine of x, okay? And this guy below here is sine of x, right? So it's good to, sort of get these labeled properly at the very least. And the idea here is that, the radius of this is from this point. It's essentially from this point, -1, all the way, to the top, right? That's the outer radius. Okay. We know that our formula is pi times, pi times the outer radius squared minus the inner radius squared dx. So this, from here all the way up till the outer radius, the top guy, that isn't just cosine anymore. It would be cosine if we were traveling from the x-axis to the top guy. Then it would be cosine, right? But the problem is that we're not traveling from here to here. We're actually traveling from here all the way here. So we're actually one behind where we want to be able to say that it's cosine. So we're offset. It's kind of like if you're starting a race, if you're starting a race here, and the starting line is actually right here. That's where everyone else is. So you're actually offset by 1, right? You're -1 behind where you should be, which is 1. So I mean, what do you do to take into account that fact, right? You got to move 1 step up, basically. And so that's the approach that we're taking here. In order to get to cosine, I can't say it's cosine because it would be cosine if it was from here to here, but it's actually -1, right? So for me to get to cosine, I have to add 1 back and then go to cosine. So it's actually just the outer radius. The outer radius is pi. So it's what I gotta do is I have to add 1 back and then get to cosine. So 1 plus cosine of x squared minus the inner radius. So what's the inner radius? Well, the inner radius is sine, right? The inner radius is sine, but the idea is we're not starting from here to here, so we can't just say it's sine. We're starting 1 lagged behind, right? So it would be -1. We're starting from -1, so we want to add 1 back and then say it's sine. So we're going to say, it's 1 plus sine of x squared dx. And we already know that we're solving this from 0 to pi. Therefore, this is the integral, if I can get it. This is essentially the integral that we would be taking in order to solve this problem. And the problem is clear, but the method is sort of somewhat elusive. So what I'll suggest is, okay, let's distribute 1 plus cosine of x squared. We can write as 1 plus cosine of x, 1 plus cosine of x. So I'll say this is 1 plus cosine of x. So 1 plus cosine of x, and then cosine of x again, right? Then plus cosine of x squared. So it's 1 plus 2 cosine of x plus cosine of x squared. So this is what we have for that guy. We have pi 0 to pi, 1 plus 2 cosine of x plus cosine squared of x. That's what we have. And then what about the sine? Well, if you do it for the sine, you're going to get the same thing, right? If this was a sine here, then you would get the same thing. You'd get 1 plus 2 cosine of x plus cosine squared of x, except the cosine of x's would actually just be sine of x's. So you'll actually get, if you do the foiling on 1 plus sine of x squared, you'll get 1 plus 2 sine of x plus sine of x squared. Okay, so what you're really doing is 1 plus 2 sine of x plus sine of x squared, or as they usually call it, squared x. Okay, dx. And you can distribute out. You can say, okay, well, this is 0 to pi. You can say that this is 1 plus 2 cosine of x plus cosine squared of x minus 1 minus 2 sine of x minus sine squared of x dx. And the idea here is that, -1 would cancel out with 1, although that really is the only cancellation property going on here, unfortunately. So we have 0 to pi, 2 cosine of x plus cosine squared of x minus 2 sine of x minus sine squared x dx. Now, there is this formula. So what we can do is we can single out things here. What we're going to do is we're going to single out the cosine squared of x and the minus sine squared of x. We're going to single this out. And we're going to say that this singled out thing, cosine squared of x minus sine squared of x, is actually equal to something. So this is actually just an identity. Let me pull it up real quick. This is essentially the identity that we can use. So we can say that this is, this is pi from 0 to pi. And then again, this we're setting equal to cosine of 2x, right? So everything else is the same, 2 cosine of x plus, and then we have cosine of 2x, right? So plus cosine of 2x minus 2 sine of x, the dx, right? And then so we were looking at this, and this was sort of tedious to solve. But like if you look at them individually, these are not hard integrals to solve, right? I mean, we can solve these individual integrals, right? I mean, this one, what is this one, right? What's the what's the integral of 2 cosine of x dx? Well, you can pull the 2 out. It's just 2 times the integral of cosine, right? Times the integral of cosine, which we know is negative sine, right? So we have one of them, right? What about this one? What's the integral of cosine of 2x dx? Well, this is just a u sub problem. Let u equal the complicated guy, and then we'll take the derivative of both sides. It's just 2. We take du over dx. That's what the derivative of that is. And then the derivative of the other side is just 2. And then we solve, we get the dx alone. So you maybe multiply dx on both sides like that. And then maybe say that dx equals du over 2, right? And then maybe you'll substitute this, the 2x we set was u. And then, well, what does dx equal to? What was this guy? Well, it's du over 2. So du over 2, right? And what's the integral of cosine of u? Well, it's the same thing as the integral of cosine of x, which is sine of x. So this is actually just sine of u over 2. And then we put the u back, which is 2x. So this is actually equal to sine of 2x over 2. So we got that guy as well. What's the integral of this guy, right? What's the integral of negative 2 sine of x? That's just doing negative 2 sine of x. I can actually pull that negative out as well. I can say that that's negative 2 and then sine of x dx. And then, I mean, that's just the integral of sine of x, which we know is negative cosine of x. So it's just positive 2 cosine of x, right? So we merge all of these guys together. We're going to get the integral from 0 to pi times pi, of course, multiplied to the integral of 2 cosine x, which is negative 2 sine of x. So maybe we can put that there. 2 sine, actually, can't do that. Negative 2 sine of x, and then, multiplied by cosine, the integral of cosine of 2x, which we said was sine of 2x over 2, plus sine of 2x over 2, plus, or why am I doing this? I mean, this is the answer to the integral, right? 2 sine of x plus sine of 2x over 2, plus the last guy, which is 2 cosine x, evaluated on those bounds of 0 to pi. Okay. So that's the idea for this one. And then, you'd actually go through and, you'd go through and it's a good thing that they have the 0 there. Although I don't necessarily think that I don't necessarily think that the 2 is negative, right? I mean, because the integral of cosine is in fact the integral of cosine is just sine. So it wouldn't actually be negative. It would actually be positive here. So positive 2 sine of x, and then sine of x over 2, the sine of 2x over 2 plus 2 cosine of x is what we'd have. And we'd evaluate this from 0 to pi. So what we would do is we would say, okay, well, this is, you would put the top bound in first. So you would be 2 times sine of pi plus sine of 2 pi over 2 plus 2 cosine of pi, right? And then minus all of this with zeros inside of it. Then you'd solve for these individually, right? You'd say sine of pi is 0, sine of 2 pi is 0, cosine of pi is -1, right? And then you'd stretch this by plugging in all the zeros in there. And then whatever you'd get by adding all these up, you just multiply that by pi, and then that would be your answer. So I want to revisit the shells, or not revisit the shells, but I want to revisit a problem that we did. And this time we're going to do it with shells. And again, for shells, you're doing 2 pi, the volume of a solid that is rotated around the y-axis, or is rotated, is solved by using shells, is 2 pi out in the front, and then you're doing the radius times the height of a given shell. That's sort of the formula there. So if we have, let's say, y equals, let's say, x, and then y equals, let's say, x squared, we want to do something called, let's say we specifically rotate this about the y-axis. Now, again, we already know how this would look like. We have a Cartesian plane, and then we have, x squared, that's parabolic. We know that. Then we have y equals x that cuts through it. Instead of rotating it this way, we're going to rotate it this way. So how would that exactly look like? We're going to have something like this, right? Where it's on both sides, kind of the same there. Okay, and the idea here is that we're going to use something called shells, and what shells will allow us to do is going to allow us to find the area by using something called shells. So the basic idea here is that you can draw like this, like a shell type shape inside stuff like this, and these shells, they progressively get bigger for each shell that you draw. So you can think of it like, you have one shell, and then the next shell you draw is substantially bigger than that. And then the next shell you draw is even bigger than that. And so, these shells, they progressively get bigger and bigger and bigger, or smaller and smaller and smaller. But it's kind of like it's kind of like one of those Russian, nested dolls, right? Although that's like a potato, but you get the idea. And so this curve here is y equals x. This curve below here is y equals x squared. The squared one is the parabolic one, right? It's not linear. And so when we're looking at this formula, 2 pi, r times h dx. So let me ask you this. What will give us the value for the radius? So again, when we're looking for the radius of these shells, we're really trying to find, what is, that did not go well. What is this length here? That's kind of what we're looking for in terms of shells. What is the, how can we find the radius of any given shell? Well, it's the distance that is being stretched along the x-axis. So it's kind of like, for this shell, this is the radius, right? It's this distance along the x-axis. For this shell that we drew up here, it's the vertical distance, the horizontal distance is that distance that we stretched, right? So it's like that. And so the idea is that, it's given by, it is given by 2 pi r is the radius, which we're going to call x. It's given by whatever x value you put in. Like, is it 4? Is it 5? Is it 6? How long is it, right? That's given by x. What about the height? What about the height? So the height, the height is kind of tricky. This time it's not just saying, oh, it's one function, right? Think we can't say it's like x, right? Because that would mean that, we're saying that this is the height from this point all the way up till this point. But we don't want to include this space down here. That space isn't even included. So why are we saying that space there? We can't say that. It's only this space here, which is the height of the shell, or this space here, which is the height of the shell, or this space here, which is the height of the shell. So hypothetically, if we had a line and we say this was 8 and this was like 4, what is the distance between both of these? Well, it's the top guy minus the bottom guy, right? That's the same idea that we're going to keep here. We're going to say, okay, well, this distance for any shell is just the top guy minus the bottom guy, and then we're going to get how the height of the shell. So it's just the top guy minus the bottom guy. So it's going to be the top guy, which is x, minus the bottom guy, which is x squared dx. Okay, and that's essentially the for the shell, right? And again, I mean, you can take x and set that equal to x squared and solve for what the bounds would be. You'll get 0 and 1. And then that's just solving the integral at that point. You're doing 2 pi 0 to 1. Let's see if we can simplify before taking the integral. That's x to the third dx. And then, we can go around and just solve the integral. So we can say this is 2 pi from 0 to 1, or, we'll just take the integral now. We'll say that this is x cubed over 3 minus x to the fourth over 4 from 0 to 1 dx, or not dx. And again, I mean, so you do this and you'd say, okay, well, I'm going to plug in the top bound first. That's just 1 over 3 minus the 1 over 3 minus 1 over 4. Minus the bottom bound. If I plug it in here and I plug it in there, I get 0. So I'm not going to even bother with the bottom bound. Then I'm solving this fraction, which is 12 for 4 minus 3, which is 1 over 12. And then 1 over 12 times 2 pi, which is 2 pi over 12. And then that's just pi over 6, right? So that's the idea with shells, is you're finding the radius, and then you're also finding the height, which is the subtraction of both of the top and the bottom functions. Okay, so what about y equals sine of x, and on the boundaries x equals pi to x equals 0? What do we do in this case? So if you're familiar with sine of x, I mean, sine of x, it's a sinusoidal wave that looks like this here. And the idea is that we only want to go from, like, these are our 2 points. This is the bounds, right? That you got, one is 0, and then the other is pi, right? I mean, we know that pi is here, right? And what you're doing is you're taking this area here and you're revolving it around the y-axis. So I should have specified, but that's exactly what we're doing. We're revolving it around the y-axis. And so inevitably what we have when we do that, something like this mountain looking thing, and the idea is that we use shells. We use shells to do this. And it's perfect for shells. We're around the y-axis. It's very dependable, at least I think in our class, to use shells around the y. And as you can see here, there is no restriction now because the height is clearly just the function, right? The height is clearly just the function. That function is sine of x. So we can say the height is sine of x. Before we couldn't say that. Before we couldn't say that because up here, the height of the shells, it didn't originate from the bottom. You can't originate from empty space, right? So over here, it's a little different. And, we start from here and then we go to the top like that, like this. And so, for each shell, it seems to be like it's just whatever the sine of x is in terms of the height. What about the, the radius for each of these shells? Well, the radius originate from here and you go here. That's just the vertical distance, right? If I had a shell like that, right? I mean, that's just the vertical distance if I wanted the radius. It's just, if I had a shell here and I'm going from here to here, it's just like, and I had a number line that could tell me, well, I just want this distance here, and that is governed by X. So that that distance or the radius really is equal to X. So we're doing the integral from 0 to pi. I mean, those are the bounds after all. From what we're doing, x times sine of x dx. Okay. Now this is, again, so remember the formula that we had for the cylindrical shells was 2 pi r times h. Now we have the r with the radius, it's governed by x, and the height is governed by sine of x. But what about that 2 pi though? Right, so we need that. And the idea here now is to just say, okay, well, this is an integration by parts problem. So you want to treat this as an integration by parts problem. We're familiar with the Lyat rule, where whichever comes first, logarithmic, inverse, algorithmic, trig, or exponential, right? Whichever comes first is the u. I don't see any logs here. I don't see any inverse trig functions, but I do see an algebraic first. So the u is equal to x. That's the algebraic guy. And when you're doing these, you do du, you take the derivative of that, which is just 1, but you attach a dx at the end, always. And then dv is just the other guy you didn't choose, which is sine of x. And then v is equal to the integral of dv. It's equal to the integral of dv. Now, what is the integral of dv? That's just me saying what's the integral of sine of x. And what's the integral of sine of x? The integral of sine of x is negative cosine of x. So v is actually negative cosine of x. And then we have this rule, u du equals u times v minus the integral of v with respect to du. So we do u times v, which is just doing x times negative cosine of x. Then we do minus the integral of v, which is, again, negative cosine of x. And might as well just make that positive, with respect to du. So we put the du down, which is just dx. And so we know that this is just x negative cosine of x plus the integral of cosine of x dx. And the integral of cosine of x is sine of x, which means this is negative x cosine of x plus sine of x. And then we're evaluating this on 0 to pi and then multiplying it by 2. So by now the rodeo is x cosine x plus sine of x from 0 to pi. And then whatever we get from here, we multiply that by 2. Let's take a look at another shell problem. This time we have y equals ln of x around the y-axis. Okay, we want to also remember that for this problem, we're given that x equals e. Now, e is nothing. I mean, people see e, they get scared. E is just, if you put in the value of e, you'll get a letter. But if you do e value, then it'll know you're talking about, okay, apparently that's a website too. But if you do e exponential value, you're going to get 2.718, right? So that is going to be, so this is going to be 2.718, okay? And so ln of x, if you're not familiar with it, it looks like this. It barely touches 1 here. Or it does rather. There's an asymptote at 1. Okay, it kind of just goes like that. There's an asymptote there, and we are cutting it off at e. So e is some value, some x bound. Let's say it's here. If 2.718 something is here, then e is there. Okay, so we're cutting it off at e, and so this is the area that we're looking at, and we're revolving it around the y-axis. So how does that? How does that look? Once we're done with it, once we're done revolving, well, it's going to be like, we have this guy like that, right? Sort of revolve that shape around. And so that would be like kind of the shape. Again, we're around the y-axis. Let's use shells. and then we shouldn't have a problem. So with shells, I mean, if you're thinking about shells here, the height of each of the shells is just ln of x, right? It's not offset by anything. So the height of each of the shells is ln of x. And as each shell grows, its radius will be governed by the x value, right? I mean, you have one shell and then the next shell, it just grows. And then its height will be ln of x, the function itself. But as it grows, the radius is going to sort of be matching what the x value is at that point. So the height is ln of x, but the radius is actually just x, right? So what do you have? We know that it's 2 pi times the integral of r times h dx. That's the formula for shells. But then what you'll do is you'll take the radius, which is x, times the height, which is ln of x, dx. U is equal to, so this is, again, I mean, what is this, right? This is and again, what are the bounds as well, right? You're going from 0 to e, right? I mean, those were the bounds that were specified. And so this is an integration by parts problem. Let's pull out the Lyat rule again. Logarithmic, inverse, algebraic, trig, exponential. Which one comes first? Is it logarithmic? Yes, we see a logarithmic first. We can't say it's algebraic because that came second. So we're going to say u equals ln of x. And again, du is going to equal the derivative of that, which is 1 over x, but remember to attach a dx. And then dv is what? dv will be the other guy you didn't choose, and the other guy we didn't choose was x. And then v is equal to the integral of that. And if we take the integral of x dx, it's x squared over 2. Therefore, this is x squared over 2. And then we pull out the formula. It's very textbook. U du equals u times v minus the integral of v with respect to du. So u times v is just doing a crisscross here, where you have ln of x times x squared over 2 minus the integral of v. So the integral of v is x. So we want to take the integral of x squared over 2, but then we got to put the du as well. So the du is 1 over x dx, right? So we got to do some simplification here. We have ln of x, x squared over 2, minus these x's cancel out. You're left with x over 2 dx. And then you take the integral of this. So you're left with ln of x, x squared over 2, minus, so you can pull out the 1/2. You're just left with doing the integral of x. So this is ln of x times x squared over 2. Minus 1 over 2 times x squared over 2, because you took the integral of x. And then you're left with the ln of x, x squared over 2, minus x squared over 4, evaluated on the bounds of 0 to e. And when you're done plugging those in, top first, bottom second, you can just multiply that, whatever you get, by 2 pi, and you'll have your answer. So let's take a look at this problem here, where we have, it says, use the method of cylindrical shells to find the volume of the solid generated by rotating the region, so on and so forth. So, I mean, so you could figure this out, without looking at a graph, and really most of them you could, right? I mean, you have e to the x, which looks like that, and then you have negative e to the x, or e to the negative x. And so it would sort of be, it would sort of be the opposite, right? And then it's bounded by x equals 1. So you're really looking at that shape there. And of course, that drawing really doesn't suffice. But nonetheless, this is what we have. This, hopefully, we can shorten it down. And that's essentially our task now. I mean, this is the region that we're concerned about rotating. We're going to rotate this region around. So it's kind of like we're going to have a bow tie of a solid, right? We're gonna be like this. We're going to have this going on. What's going on there? We're going to have like a bow tie of a solid, right? So it's going to be kind of like that. We're going to rotate it around like right? We're just kind of going to rotate that around like that. And then it's gonna sweep through from the back and then create a whole solid for us there. And then that's bounded by, this line x equals 1. And this, so, but the idea is you want to be able to distinguish between them, right? In order to identify, what your cylindrical shells are. And if we look closely, we would kind of have something like this on the other side. It's sort of replicated, right? When it sweeps through. And when you have a shell, for any given shell, right? For any given shell, for any one of these given shells, the height would be, again, it would be the difference between the top curve and the bottom curve, right? And that bottom curve is e to the negative x. I'm sorry, this blue curve here is it's e to the x, right? And that bottom curve, that distance, that bottom curve is e to the negative x. So it's going to be the bottom curve. It's going to be the top minus the bottom, right? So that's the height of the cylindrical shell. It's just like taking a rod and being like, okay, well, that's 8. And this is 4. What's the difference between them? Well, it's 4. Kind of like that, except this guy is 8. And this guy down here is 4. We want the difference between them. Well, it would be 8 minus 4, right? So that's the height, is e to the x minus e to the negative x. And then as these shells grow, what will tell us how they grow on the x or across the x-axis? That horizontal length that we want is governed by x. So the radius is going to be x. So if we set our integral, we know that for any of these problems, it's 2 pi rh dx for cylindrical shells. We'll take the 2 pi out. We're going from 0 to 1. It's just the radius. Okay, what's the radius? The radius we said was x, and then we have our height, which is e to the x minus e to the negative x, and then dx. Okay, how can you sort of make this easier on yourself to take the integral of something like this? Well, it's x e to the x minus x e to the negative x. So maybe we can distribute, see if that helps us. And then we can sort of just take two separate integrals. So it's just 2 pi 0 to 1 of x e to the x dx minus the integral of 0 to 2 pi, and then 2 pi again. We're just doing one of these on both of these, right? So x e to the negative x dx. And this would then be an integration by parts problem for both of them. I'll do the first, I'll leave the second to you. So with the Lyat rule, we have logarithmic, inverse, algebraic, trig, and exponential. The algebraic comes before the exponential. So we'll let u equal x. Du is equal to the derivative of that, which is 1. So we'll just write dx at the end as well. We always have to tag that on. Dv is equal to the other guy we didn't take, and the integral of the other guy we didn't take is just e to the x, because the integral of e to the x is just e to the x. And then we look at u du minus is equal to u times v minus the integral of v with respect to du. So we do something of a crisscross there, where u times v is just x times e to the x minus the integral of v, which is e to the x, with respect to dx, which is just x e to the x minus the integral of e to the x, which is again e to the x, and that's what we have. And so that's this part, right? And then you do this part as well, and then just subtract that from that part, and then do that on the bounds of 0 to 1 for each of them. So just treat them as their own separate problems, and then combine them after you're done. So now let's cover region bounded by curves. So essentially, sometimes you'll see, they'll say, okay, well, I'm giving you a couple functions, find the region bounded by both of those curves or all of those curves. And in this case, you're not rotating them. You're actually, you could sort of plot this by hand, right? I mean, you would have, you could look at e to the x as being something like that. And then x sort of cuts through right down the middle like that, right? the idea is that it's giving you x equals 0 and x equals 1. So from 0 to 1, right? It wants you to essentially find this area here bounded by e to the x and x. So bounded by this curve, can you find the area? And again, I mean, these problems, they're not too bad. And you can see that we have a representation of it. That doesn't work. What am I doing wrong? Y equals e to the x and y equals x. Yeah, I mean, it should sort of produce. Is it? Yeah, okay, my bad. So when you plot this, this is actually what you tend to get. You'll get this e to the x, and then you'll get this x guy. And essentially what's going to happen is that they are going to, at one point, they're gonna, what's it called? If they're not really going to intersect as such, as you can see on the graph, but the idea is that the problem makes it such that, you know, oh, you have this x equals 1, that means you need to cut it off here. Okay, and if you cut it off here, this is what you're looking for. You're looking for the area between both of these curves. This is the area between both of these curves that you are looking for. And so in order to solve this problem, you actually just take the integral of the top minus the bottom. Okay, so the top function is e to the x and the bottom function is just x. So you take the integral of e to the x minus x dx on the bounds that you were given from 0 to 1. And then you're just solving, so you can break this up. You just e to the x minus x squared over 2 from 0 to 1. Plug in the top bound first, that's e to the 1, which is just e minus 1 over 2. Subtract the bottom bound, which is e to the 0, minus 0 over 2, which is 0. So it's just e to the 0, which is 1. So it's e minus 1/2 minus 1. So you'd work this out, and then that would essentially be your answer. So let's look at the area of the curve between y equals x squared and y equals 2x minus x squared. As you can see, this is what we have here. It's an area bounded by the curve. And again, I mean, like, to find the bounds, you could set them equal to each other and then solve. And then you'd be able to solve what the bounds are. But I mean, so like you can clearly see that this is a, you know, this is clearly an area bounded by a curve. And so we take, again, you take the top guy and you minus off the bottom guy, dx, on the bounds that were specified. And in order to do this, you would essentially just say, okay, well, you know, this top bound is 2x minus x squared. So you'd come down here, you'd say, okay, well, this is 2x minus x squared minus the bottom bound, this line here, which is x squared dx. Can you simplify before taking the integral? It won't hurt if you can't. It's still going to come out to be the same thing, but you can though, right? Okay, and then you take the integral of this on these bounds, 0 to 1. And again, you could solve for that by setting them equal to each other. That's 2x squared over 2 minus 2x cubed over 3, evaluated from 0 to 1. If you put 0 in there, you know, this becomes 0, this becomes 0. So, you know, your second term is 0, but if you put 1, you'll have 2 over 2, which is 1, minus 2 over 3. So it's 2 over 2 minus 2 over 3, which is 1 minus 2 over 3. Now let's take a look at what we're given here. So this is sort of a funky graph. You have two you know, curves where you have cosine as it normally tends to run. Then you have one minus cosine, as you can imagine. That would be a little different. And what we're trying to find, interestingly enough, is from 0 to pi. So we're cutting off the line right here, and we want the area of this portion. But in addition to that, we want the area of this portion. So how do you do stuff like this? Well, I mean, let's take, I don't know, let's take sine and cosine, right? Like what if I said, okay, I want the area up until this point? Well, that would mean that you have to get me the area here and you'd also have to get me the area here. Okay, so the idea is you break it up, right? See, the problem is this is cosine of x right here, then this is sine of x. So when you do this portion, you're actually doing the integral of the top minus the bottom, cosine of x minus sine of x. But then when you do this portion, it switches around. Sine of x is the top guy and cosine of x is the bottom guy. So what you'll have to do in order to combat that is you're going to have to add from this point to this point. So then it switches around, sine of x plus cosine of x. And the same idea is happening here, where this blue curve is clearly cosine, right? So you would eventually do the top minus the bottom one, this curve right here, which is 1 minus cosine of x, right? And then you'd add that to, so that's like one area, right? And that comes about to being cosine of x minus 1 minus cosine of x dx, which is minus 2 cosine of x minus 1 dx. And then the other area there from this point to all of this, right? You're adding on, and this integral would be taken from 0 to pi over 3. And then the next guy, you'd start from this bound of pi over 3. You'd do it from pi over 3 to pi, right? All the way to where we want, to pi. And then instead, now the top and the bottom change. So instead of it being 1 minus, instead of being cosine being the top here, it's actually 1 minus cosine. So it's actually 1 minus cosine of x minus cosine of x dx. And so, you basically take these integrals individually and then add them together. And then that would essentially give you an answer. So you have pi over 3 to pi of 1 minus 2 cosine of x dx plus this portion here. And that would be your answer.